and welcome to my presentation. First of all, let me thank organizer for this wonderful seminar. So I am Ovgun from Eastern Mediterranean University, and today I would like to talk you about the shadow and deflection angle by this new Symmergent gravity theory. So in 1919, the Eddington and Dyson led a solar eclipse expedition that measured the deflection of light by the sun's gravity, which providing the strong evidence for Einstein's newly formulated general relativity theory. And after a century later, in 2019, the Event Horizon Telescope collaboration released the first direct image of the black hole, especially the supermassive black hole at the center of the M87 galaxy. And this image was made possible by the extreme light deflection caused by the black hole photon rings, which cast a shadow in the surrounding matter. And these two events a century apart, both providing a crucial evidence for our understanding of gravity and also behavior of space and time in the presence of massive objects. So after the observation of this shadow image by the Event Horizon Telescope, this opened a new era of observational astronomy to probe and test gravity and fundamental physics in this strong field region. So it is commonly believed that the gravitational field around the astrophysical compact object is described by curved black hole geometry, and this Event Horizon Telescope data therefore can be used to test this hypothesis and put constraints on space-time geometries which deviate from the curve. And we will consider black hole in modified gravity theories, especially Symmergent gravity, and we will discuss whether how they are constrained using the Event Horizon result of M87 or recently found Sagittarius A. So here you can see the properties of these two black holes, and I am showing the right here. This is trying to give you a summary of how different black holes might appear if you were to image them with the Event Horizon telescope. And the idea here is that on the y-axis, I'm showing you the flux of each of these black holes at 1.3 millimeter, which is a wavelength that Event Horizon telescope observe, and the x-axis is the showing the resolution that the telescope, at least in this current configuration, will able to obtain. The point here is that as you go towards the left on the x-axis, you get the higher and higher resolution, so that this Sagittarius A and M87 are very clearly the two best candidates for us to get a horizon and image that is the result to horizon scale. But all of the sources in this purple triangle, you can see here on the side, these are the sources that are bright enough for our Event Horizon Telescope to observe. We just won't be able to do a horizon scale science with them, so that we only focus on the Sagittarius A and M87 galaxies and black hole. And they are very important laboratory for studying the fundamental physics and also astrophysics of black hole at high angular resolution. So by using the image of the black hole shadow, you can probe and test the modified theories by checking the size of the shadow radius. Or also, gravitational lensing is one of the important tools to check the modified gravity theories and how they are deviate or change different than the Einstein gravity. For this purpose, for the studying the deflection angle and weak deflection angle, we use Gibbons and Werner method, and which is recently done. Gibbons and Werner present another approach to gravitational lensing theory, which emphasizes global properties. Specifically, they consider the astrophysically relevant weak deflection limit, not in the impulse approximation, but treat the light ray as the spatial geodesic of the optical metric, and use the Gauss-Bonnet theorem, which is well known in the well known by the mathematicians. And it turns out that the focusing of the light ray is, from this point of view, essentially a topological effect. Hence, they find that, rather surprisingly, that the deflection angle can be calculated by very simply integrating the Gaussian curvature of the optical metric outward from the light ray, in contrast to the usual description in terms of the mass enclosed within the impact parameter of the light ray. So here the topological contribution is therefore essential to focusing, and it is the sense that gravitational lensing can be understood as a topological effect. So there are a very important contribution to this method. So we also make some paper on it. So here you can see that the deflection angle is calculated by integrating the Gaussian curvature in the domain outward from the light ray, as opposed to the usual treatment. And for example, if you look at the optical curvature of the Schwarzschild black hole, approximately it is equal to -2m/r². So when you put it in the integral, you can directly calculate the weak deflection angle as 4m/p. So this is a very powerful and simple method. So first of all, I want to review this method. So another important thing is the shadow of the black hole. So light rays, here you can see the first figure by the black hole shadow, which is drawn by the hand by the luminance in 1979 with the accretion disk. They make a computer calculation, but hand drawn. So light rays near the center of black hole are expected to be affected by the luminous accretion disk or other dust that surround the black hole, and the matter causes a spreading such that the black hole silhouette is not sharply delimited. And in order to generate a more realistic image of the black hole shadow, the visual appearance of accretion disk or jets is studied with help of the sophisticated also numerical ray tracing programs by several authors. But this following by the pioneering work of Bardeen, Cunningham, and also Luminant. And after that, this picture, as you see, done in the 2000s, as a prediction of the black hole image, and suggesting that it should be possible to observe a black hole using a global network of telescopes at the millimeter waves by Falke and Melia. So how can you calculate the shadow of the black hole, and which component of the metric is important for us? So if you have a spherical symmetric metric with A, B, and C components, and first of all, you must understand the photon sphere location, and then by using the photon sphere location, you can calculate the black hole shadow radius. The radius of the black hole shadow is just the length photon orbit and only depend on the GTT component. So it's only depend on the A function and also C function here. Okay. And the photons, when entering a black hole system for different impact parameters, the photon with a critical impact parameter ends in a circular motion around the black hole, or we can say that a photon sphere is location where gravity is so strong that light can travel in a circle. So that this photon sphere is very important. So in the Schwarz spacetime, for example, if f is metric function is 1 minus 2m/r, you can calculate the photon sphere as its unit horizon at 2m and its photon sphere is 3m, but the radius of the black hole shadow is out of the photon sphere and at 3√3, which is approximately 5.2 m. But if you go to the rotating black holes, how can you guess the other parameters? So extraction of black hole spin using the obliqueness of the shadow So the shadow angular size gives us information about the black hole mass. But the second thing which we could hope to measure is the oblateness, and the oblateness can give us information about the black hole spin. As you see that this picture is not a full circle. It is important also that the deformation, this deformation from this circle, depend on the viewing angle of the observer. And for the equatorial observer, the deformation is strongest, while for the polar observer, the deformation is absent. Also, this deformation is dependent on this spin. And if you look at the curve case, generally speaking, the size and the shape of the shadow depend on the parameter of the black hole. For example, the shadow becomes deformed if the black hole is rotating, and also depend on the position of the observer. And if A is rotating parameter is increasing, the deformation is also increasing. But curved black hole shadows depend only weakly on the spin. So this is the radius of the black hole shadow. This is full circle, so there is no rotation. A is equal to 0. So if there is a rotation 0.999, then you can see that you don't have the full circle, but you have a deformed circle because of the rotation. And from the new experimental data, we can say that this result cannot place constraint on the parameter in the curve metric. So instead of studying the rotational black hole solution, we can also study the non-rotating black hole solution and check the parameters, because they find no noticeable difference for curve and non-curve images. And from the experiment, we have a 70% constraint region, and this region radius must be between 4.31 m and 6.0.8 m, and this is from the M87 data. On the other hand, if you go to the Sagittarius A Event Horizon Telescope observations, they give you 10% constraint, and radius must be between these numbers. Also, you can use the Event Horizon Telescope and black hole shadow to constrain the black hole charge, because black hole shadow size also depends on the black hole physical charge, like electric charge, scalar charge, and other charges. And using the Event Horizon Telescope 2017 M87 image, you can give constraint on physical charge of large variety of black holes. You can see that many different black holes, and in the 1 sigma region, you can see that the charge should normalize, physical charge should be very small. But when it is a small, the difference in the black hole is very difficult to see. But when charge is larger, yes, you can see the deviation from the different black holes. Yes, this is the same thing. So we can use this 17% error bond, can also use the constrained charge solution, also non-GR field equations. And by using this new Sagittarius A paper and observational data, we can use this 10% bound to constrain the charges and also other parameters. So if you want, you can check also this our recent paper, which we test more than 50 types of the black hole. So we had independently start this work before the Event Horizon Telescope press conference, announcing the new observation of Sagittarius A. And some of the model we test have also inevitably tested by the collaboration. However, in this work, we have considered other models and scenario behind those considered by the Event Horizon collaboration. And we have verified that for the overlapping models, both results agree, therefore providing a valuable and independent cross-check. And also we consider a wide range of well-motivated deviation from the classical GR solutions and constrain them using the Event Horizon Telescope observations of Sagittarius A. And this is also very important paper and very long. So you can check our constraint. For example, for the Riser Nordstrom black hole, you can see that charge should be for the 1 sigma region, we put an upper limit as a 0.8 m. If you come back to our Symmergent black holes, so thanks to the Professor Demir that we have a new theory now, and for 2 years or 3 years, we focus on this new theory to probe it by the black hole physics. So Symmergent gravity is the FR type gravity theory, which emerged in a way restoring gauge symmetries and broken explicitly by the ultraviolet cutoff in effective field theories. And to test this Symmergent gravity, we construct a novel black hole solution in 4 dimensions and study their shadow and lensing and other properties. Here, this looks like the Schwarzschild ADS or DS type black hole with the parameter S0 and alpha hat. This last term is nothing but the vacuum energy or cosmological constant term. And the parameter is this last parameter also measure of how sparse the quantum theory mass spectrum or how significantly the distribution deviate from the average mass. And this C0 is very important because it is a loop factor and it stands for the total number of the boson and fermion in nature. So this number of boson and fermion involve the known particles, quark, leptons, photon, gluons, and big boson, as well as completely new particle maybe, which we don't know. And here we also show which range of the parameters give the black hole solution and no black hole solution. So after that, with our collaborators, we published a paper this year and study deeply the other properties of the black hole shadow and also the other quasi-periodic calculations. And here, the light blue regions make the metric a true black hole metric, but the white regions are the ones that don't lead to the black hole solutions. After that, we show that we can also observe that the Hawking temperature and effect of the generalized uncertainty principle of this Symmergent black hole. So here you can easily see that how alpha and C0 theorems change the Hawking temperature clearly, because there's alpha is here and C0 is here. So it is different than Schwarzschild case, of course. And one can observe that the temperature exponentially increases with varying mass, and also it is changing, it is increasing also varying the alpha parameter. And also by using in various type of theories of quantum gravity, the main feature is the presence of minimal noticeable length. In order to study this minimal length, the generalized uncertainty principle is the most appropriate way, so that by using the generalized uncertainty principle, we study the Hawking temperature of this Symmergent black hole, and we check also how this beta theorem, which is coming from the quantum gravity, affect the also Hawking temperature. The Hawking temperature decrease as we increase the value of correction parameter beta. So when beta is increasing here, you can see that the Hawking temperature is decreasing. Also, recently, with our new paper, which is under review now, we calculate and derive the charged black hole solution in the Symmergent gravity theory. And we check also how this additional charge affect the Hawking temperature. As the figure reveals, Hawking temperature decreases slowly with the decreasing black hole charge. On the other hand, we also look at the shadow of the black hole and its with deflection angle. Here, you can see that it is you can easily see that on the left side we did it for the Sagittarius A data, and on the right side we did it for the M87 observational data, and we try to find a constraint to the C0 value. We should then see how the influence the deviation, the shadow relative to the Schwarzschild case. And for example, you can see in the 1 sigma region, shadow radius is constrained to the alpha. Here, instead of alpha, we say A value, and you can see what should be the C0 values. Okay, so you can say that this A and C0 values are in the allowed region. And if you look at the approximately shadow radius of the Symmergent black hole, normally the Schwarzschild black hole has 3√3m, but for the Symmergent black hole, there is some extra theorem which is coming from the effect of the loop factor C0 and parameter A. Okay, this is also here you can also see the effect of the Symmergent gravity on the shadow. And also we calculate the with deflection angle using the Gauss-Bonnet theorem, and we plot the alpha versus impact parameter B for different values of the Symmergent parameters A and C0. And here the figure shows that the exact formula as a function of the impact parameter B for nearby observer, and the Schwarzschild case is for the black curve, and it is, you can see that the deflection angle as expected decreases monotonically. We observed that also at the low impact parameters, the DS and ADS Symmergent behavior is nearly identical, so you cannot see their differences. But if you go to the higher impact parameters, the deviation is a bit large. After that, we also construct a rotating curve ADS-DS type Symmergent black hole solution, and then we study its behavior and its effect on the shadow radius and also lensing. So here we, in our plot of the photon sphere radius for the rotation Symmergent black hole, first you can see that the location of the photon sphere along the equatorial plane. As you would expect, the Schwarzschild case, the photon sphere at 3m, but the Kerr case is different. And you can see that for the small r, the difference is very small, but when r is increasing, the deviation is also very slightly different. So you can use it to also guess the effect of the Symmergent parameters. So if you look at the plot of y and x for the shadow of the black hole, here we take the rotation parameter as a 0.90 m, and overall we observe the D-shaped nature of the shadow, which is expected for the rotating black hole, cast to the spin parameter. So as photon travel in the intervening space under the effect of the Symmergent parameter, the shadow size as seen is increasing. So if you compare, for example, for the constant alpha, C0 is minus 0.50, but when C0 becomes -1, it is increasing the shadow size. Also here, in this plot, we make a shadow radius versus A parameter, and you can, when you zoom it, you can see easily how the shadow radius is changing. The change is very slowly. So again, if you compare our result with the M87 and Sagittarius A observations, based on this figure, we conclude that the parameter we used in describing the shadow cast fall within the upper and lower bound at 1 sigma level here. And for the M87 here, you can see that they are in the 1 sigma region. where this happens, the range in C0 is more extensive in M87 than Sagittarius A. And we also observe that the less negative C0 introduce more sensitive to deviation than more negative C0. So that's why we take here the C0s are mostly negative values. Also, if you look at the deflection angle by the Symmergent black hole, the solid curve here represents the photons co-rotating with the black hole, while the dashed curve represents the counter-rotating photons. And the results show that the co-rotating photons produced with deflection angle at lower impact parameters compared to the counter-rotating photons. And here also we find that the Symmergent parameter, this C0, which is a loop factor, has an important effect on the result of the weak deflection angle, and also, as I show you, the shadow of the black hole. So similarly, this time, and in our also recent paper, we construct a charged, which is rather than also DSA, the Symmergent black hole, and this paper is also under review. And here also we check what happens if we add an additional charge to the shadow of the black hole and also the lensing. And you can see that the allowed 1 sigma shadow radius band is in the 1 sigma region, and it is in the allowed region for these values. And also similarly, if it is same for the M87, but for the M87 on the right side, there are more values are in the 1 sigma region here. And somehow the effect of also DS and ADS cases become hard to distinguish as C0 gets larger in the size, because the difference is very small. And separate paper, we also look at the triangulation of this image, and we also look at the energy flux, variation of the energy flux with the radial coordinate, and also variation of the differential luminosity with the radial coordinates. And this paper is also now under review. And we, as C0 approached infinity from both of the positive and negative side, the values of the flux and also luminosity are all approach to the Schwarzschild value asymptotically. As C0 approach to the 0, like here or here, and from the positive value, the net flux and also luminosity decreases. And this is due to the inverse correlation between the C0 and the cosmological constant lambda theorem. Here also we observe some significant deviation from the standard Kerr or Schwarzschild cases. So by changing the number of the boson and fermion, it affects the shadow size and also flux and luminosity of the black hole. So what will happen to the black hole when it's perturbated by external factors? This is also one open question, and we have now working on it with our collaborator. So we know that a perturbated black hole will go through quasi-normal modes, ring down, and it's the aim of our ongoing project to calculate this quasi-normal modes and also gray-body factor. And this is also one of the important questions. And our other project is, are there any neutrons in Symmergent gravity? So this is also what we are working on, because investigation of the effect of Symmergent gravity in other astrophysical objects, also it could be possible to test the Symmergence in other astrophysical objects, such as, for example, a neutron star, maybe boson star, maybe Proca star, or other compact star. And such tests can be useful to extent one has a precise knowledge of the density and also pressure of the astrophysical object. And as a summary, this horizon scale image of supermassive black hole and their shadow have opened a new unparalleled window onto tests of gravity and also fundamental physics in the very strong field region. So by studies of Symmergent gravity in relation to black hole have started a novel research direction. So this is a new theory, and it is good to that this theory is a bit similar to the FR gravity theory. So you can do whatever you want by using this Symmergent gravity. So there are many infinite opportunities. And here we show that in our papers, we show that the size and shape of the shadow of Symmergent black hole is consistent with the prediction of by the Event Horizon Telescope observation. And we use this observation to constrain the loop-induced parameter of the Symmergent gravity, and also constrain this number of boson and fermion in the universe. As a future, it looks bright, so additional telescope will improve the image fidelity and may allow us to measure the shadow asymmetry. And the first image of M87 can be used to measure the radius of the black hole shadow within the 17%, and image of the Sagittarius A within the 10% region. And these error bars also can be used to constrain modified gravity black hole, as we did. And these constraints are about 500 times more stringent than solar system plans, and also comparable to LIGO-Varigo constraint. So studying shadow is now better than studying quasi-normal modes or ring downs or gravitational waves. So the future is bright and should be able to perform better tests in the future. So thank you for listening.
Thank you so much, Prof. Ovgun, for that wonderful talk and the detailed explanations of your results, as well as the future prospects, which seem very, very interesting. So questions for Prof. Ovgun. I see Prof. Ma's hand up.
Yes, I have several questions. Can you go to the early slides, which you show the Event Horizon Telescope resolution and also flux? Yeah, that triangle. Yes, I didn't quite catch up. Why does the upper right triangle can't be observed, and also the lower part, lower of the plot can't be observed?
Yes, here I'm not expert of the experiment observation, but as I know that here these stars in the triangle is very bright, so that this Event Horizon Telescope cannot observe them.
But why? I mean, if it's bright, it's more obvious, right? More luminous.
Yes, more luminous. But for example, when you see something too bright, for example, if you imagine you can take a telephone and try to take a photo of the sun, or
okay,
if you try to take a photo of the lamp, can you take a photo? No, because the lamp is too bright. So it's something like that, maybe.
But if I see the flux, they're on the same level of flux, the same level y-axis at the Sagittarius A and M87. So,
but also the important is the Event Horizon Telescope resolution. But if you look at it, there are radius of the shadow is very larger. Did you see here?
Yeah, but if the shadow is larger, then that's easier to observe, right?
But our Event Horizon Telescope resolution should be at closely here 1 and this side.
Well, I don't understand. If the shadow is bigger, then it will be easier to observe, right?
But also the location of the black holes are important. Now I don't know exactly the location of this galaxy or black holes.
Okay,
this is one of the reasons.
Okay, could be, yeah. And you have another slide at later stage about Hawking temperature.
Hawking temperature, yes. Yes.
No, I think later slide.
Okay.
Yeah, here. First of all, I see there is this modified, this upper thing, which is a modified Heisenberg uncertainty principle. So what's the reason of this beta, which seem to be a second order correction? this part.
Here, if you look, check in the literature now, there are many papers on the general uncertainty principle. So when beta is 0, as you see that it's reduced to the normal uncertainty principle. So, and they guess that maybe there is a very small deviation from the.
But what's the physics of this term? I didn't.
Yes.
What's the physics?
Yes, this beta give you some minimal length of the theory. So if you want, I suggest you to check the literature for it, because it is a very long thing. First, it is done by who did it in 1990s. They did it. So,
but then the beta is must be some dimensionless constant, right? Because you add 1.
This is constant. I didn't write it here, but yes, this is constant related to also Planck length and Planck length.
Okay. And the other thing is on the right here you have a Hawking temperature negative. Why is that?
Yes, if you take this here. If you take this C0, it's positive. Yes, unfortunately, you can find the Hawking temperature negative. So this negative.
But what's
okay? This Hawking temperature negative is not a very common thing, but when you look at the Hawking temperature from the wormholes, you can find this kind of things.
Normally, because temperature can only be positive, right? Why does temperature negative?
Normally people are neglected, but here we said that okay, this is also another possibility, so let's also at this range, and here also you can easily see that to find the positive Hawking temperature, you must choose C0 negative.
Okay, so it's just a mathematical branch of solution. It has no physical.
Yes, there's no physical.
Okay.
Okay. Thank you, Prof. Ma, for those questions. Does anybody else have any questions for Prof. Ovgun? Yes, Prof. Hansraj.
Thank you very much, Prof. Ovgun. That was very illuminating. We enjoyed that presentation. I learned quite a lot from that. I'm wondering, now that you've done the work on black holes, what's the prospects for work on, let's say, stars? Because with f of r, with the quadratic nature of the terms, it makes solving the equations quite complicated. Do you know if many works have been done on just ordinary stars, even neutron stars and so on, white dwarfs?
Yes, there are, you are right, Professor Stan. There are few studies on the FR gravity and modified gravities, and it is very difficult to find analytic solutions because of these TOV Boltzmann equations, but we try to find some numerical plot of the mass and radius curve. And yes, we have the also Einstein equation of motion for this model, and also for the Boltzmann equations. And now we try to use different equation of states and make this numerical plots. Yes, in the literature, there are some few studies.
May I also say a word here, if possible?
Yes.
Yeah. Also, in this, if you think of this Symmergent gravity, in this approach, there is a plethora of new particles needed for inducing Newton's constant correctly or Planck scale correctly. And these particles do not have to interact with us. That means that they can form a dark sector, which might be the explanation for dark matter. Actually, this 25% of the universe is composed of this thing, and we don't have even a single evidence in collision experiments or direct searches. But actually, we know that they exist. It exists through the gravitational observations. That means that there can exist such a dark sector. In this dark sector, we can have dark stars. dark galaxies or even dark, let's say, compact objects, so to speak. And in that case, solutions of the equations will involve not only the usual tau equations involving neutrons, protons, and known particles, but they may involve even massive dark particles, so to say.